ventilators, to be honest, and exactly how would one go about if they wanted to make a ventilator, what are the challenges and the problems. Before I introduce our speakers and talk a little bit about our topic today, I just wanted to share with you إنه our LAU mobile clinic اليوم كانت بعلبك بالهرمل بالقاع ببريتال بدال الأحمر براس العلبك. So hopefully if any of you live in that part of the world, إن شاء الله تكونوا استفدتوا من our free services so you can get yourself tested and hopefully your results will be negative. Please تابعوا as well the mobile clinic to see exactly when راح تكون عم تقروا in order to check when will the clinic be in your area. Now, as for today, guys, عندنا 4 speakers to be honest, so something a little bit different to what we've actually been used to. Or one of our speakers, ما بدي أقول our speakers, لأنه honestly أنا بعرف اليوم. So one of our speakers, Dr. Barbar Akle, who is the assistant provost and the associate professor at the School of Engineering. Barbar has a PhD in mechanical engineering from Virginia Polytech Institute, and his main research focuses on modeling and applications of smart materials, including solar vehicles. Our second speaker is Dr. Michel Khoury, who is a professor in the School of Engineering, and at the same time, he is also the associate dean within the School of Engineering, and he has a PhD in mechanical engineering as well from LAU University in the US. Our third speaker is Mr. Paul Abi Nasr, who is the CEO of Polytextile Industrial Complex, and Polytextile happens to be an incorporation or a company that is actually in collaboration with LAU on the project that you guys will be listening to today. And our fourth speaker is Dr. Ali Ammouri, again from the School of Engineering. He is also a holder of a PhD degree in mechanical engineering, and his work mainly focuses on machining, industrial automation, and computer-aided design. Now, very quickly, our topic today is going to take you, or our speakers today, guys, are going to take you through the entire journey and the challenges along the way when you want to go about to build an open source ventilator, well, for one particular purpose, in this case, to treat patients that are associated with COVID-19. Now, as I already mentioned, this project is actually a collaborative project. So in addition to Polytextile Industrial Complex, the LAU Medical Center is also, well, LAU Medical Center Rizk Hospital is also part of this project, and School of Engineering at LAU as well is part of this project, and the School of Medicine at LAU is part of this project, and American University of Beirut Medical Center, as well as S&AS controllers. So Barbar, Michel, Paul, and Ali, who would like to actually get started on this presentation, so you can have the floor.
Thank you, Robin, for your nice introduction. Hello, everyone. Hopefully today we'll have a nice presentation regarding our 1-month-old ventilator. It's been actually more than 1 month, a little bit more than 1 month. We've been working on that ventilator. It's a pretty sophisticated ventilator that we believe hopefully it will never be used, but we believe in the future, and especially if there is a round 2 for COVID-19, it will be a pretty useful device. The idea of what we're building is an open source ventilator. So the main target is we don't want to have any commercial profit out of it. It's a good cause, so that globally anybody in the world can use that ventilator. The project started almost a month and a half ago. I think everybody, whenever we started to hear about COVID-19 and when COVID-19 started to hit Lebanon, we were pretty concerned about our safety, and we learned that we have minimal amount of ventilators for hospital systems. So this is where everybody rushed to really create ventilators. And for us as engineers, we definitely also looked into that very, very fast. And over some connections, we realized that there are so many groups in Lebanon trying to build ventilators, and this is where we got in touch with Mr. Paul Abi Nasr from Polytextile. Paul is actually behind me, and he is very enthusiastic about this project, and we got really together with that. We engaged so many groups, but finally the project was completed really between LAU, the School of Engineering, and LAU, the School of Medicine, with LAU MC, Polytextile, and the S.A.S. controllers. We also have a good contribution from the American University of Beirut, especially Dr. Muhammad Khatib, and we also have the medical engineering unit there also supporting that project. So this is in brief how the thing started. By the way, also there's a whole group of activists that are supporting us. They started on Slack, about 30-40 activists, and it's pretty nice, and we had really nice support from them. So I want to really introduce this team. From engineering, we have Dr. Ali Ammouri and Dr. Michel Khoury, and myself from LAU. Dr. Faiz Abillama is the medical expert from the School of Medicine at LAU, and Paul Abi Nasr from Polytextile, and Ziad Bustani from S.A.S. Right now we are in, by the way, the simulation center at LAU. We are testing the ventilator. As we are going to move forward with that, we will show you the whole component. We'll show you how it works and how we came about designing it. And just a couple more things before I give the floor to Paul to discuss ventilators in general. I want to say that we wanted to be open source. We wanted to be robust. We wanted to have a ventilator that actually saved lives, because we've seen so many ventilators out there that we are afraid they won't save life. There's so much demand for what the ventilator can do, and it's not that simple. Also, we built it out of components that are widely available, mostly industrial components that fit the medical profile, so they are safe for medical use. And of course, we built it from, we had to do 3D printing, we had to do so many things because some critical components for ventilators like sensors and modulating valves, we started to notice that they are becoming very short globally. So this is where we decided to really design these sensors, and we will be talking also about that. Without further ado, I'm going to go ahead and give the floor to Paul, and Paul will talk to you about what are ventilators in general and how we started the design. So, Paul, the floor is yours.
Thank you. So, first of all, thank you all for coming here. Typically, what we're trying to achieve is trying to tackle the issue of the ventilator. Now, what is a ventilator? Why this whole thing about the ventilator came up with the COVID-19? Well, typically, a ventilator is used whenever the patient has difficulties breathing on his own. There are different cases where it is used, but now, because of COVID-19, the usage went up dramatically. The reason behind it is that COVID-19, as an illness, as a virus, it actually hits the lungs. It creates kind of clogs in the alveoli in the lungs. It makes it much more difficult for the patient to breathe. And if left unchecked, or some patients also, even if they are treated, they degenerate to the point where they actually need a machine to help them breathe. The issue with this is that typically with COVID-19 patients, these machines will be used on a patient for a long period of time, and so typically the usage of a ventilator in a hospital environment is restrained. So normally they wouldn't need so many ventilators in the same time being used for a long period of time. So this is very important. So that created a shortage worldwide for ventilators. In Lebanon, according to the Ministry of Health, there are 1,200 or 1,300 ventilators, of which those that can be used for this particular purpose are around 500, of which 80 to 90 are, to our knowledge, they're defective and they can be repaired. So the total amount of ventilators available in Lebanon is around 400, 410, out of which 200 or so are in usage for non-COVID-19 patients. So that would be people who have the need for ventilators without being COVID-19 patients. So when we looked at these numbers, it was clear from the start that there's going to be a need for ventilators. Now, to go to the ventilator in a nutshell, the ventilator typically has a couple of operation modes. We're not going to go in details in every single one of them, but let's talk about, let's say, the main ones. There is the pressure control. So this is the ventilator. The machine will pull air inside the lungs of the patient and try to reach a certain pressure point. There is volume control where the ventilator will push air until it reaches a certain volume. Then you have something that has been written in the that has been required by the British government when they wrote the rapid ventilator requirements, which is the pressure regulated volume control. So typically they're trying to reach a certain pressure point at every cycle, with the target becoming after a couple of cycles reaching the right volume. So they try to give the right volume, which is the target of the mode, but they want to do that while going step by step with the pressure upwards and upwards and upwards. This system, this particular mode, is typically called a fire and forget mode. So typically, it helps the healthcare providers to set the machine, and the machine will improve or change the settings as the patient improves. So it doesn't need as much input from the healthcare providers, which is very important, because when it will never happen, but as we saw in Europe, they were overwhelmed, and patient time was very low, and so it was crucial for the machine to actually pick up some of the slack. Now, to go to a bit what has been proposed as designs, because we all heard there are so many designs out there, every single group in the world trying to put some design on the table, but some designs are good, others less so. Is typically the small bag type, or that's balloon type, that is used in the ambulances. They push on it by hand, and a lot of designs centered around that. Because it's open sourced. This particular design is good for transportation, for short term, but you cannot put a patient on long term with an ambubag centered design. First of all, it has limitations regarding the volume it can give. It has limitations regarding the wave form, how we're putting in the air inside the patient. Is it too fast? Is it too slow? Is the pressure rising too fast? It is very slow as a system, so it cannot react to a patient that is actually trying to cough or needs a bit more air at the same time. So this is where the problem with the ambubag is, and plus the fact that the ambubag, by definition, was not designed to run hours and hours and hours and days upon days. Now, after that, we saw NASA, Tesla, another design by MIT, the Imperial College. I mean, there are plenty of very, very good designs now out there. All of them are pretty much centered around the same concept, and that would be the concept that we also took up right from the start, because we thought right from the start that we needed to have a design that is robust enough, that can actually meet all those targets, and especially those changing targets, because this is an illness that we know very little of. I mean, it's been there for 4 months, and so the way to treat patients is changing. The doctors are changing the way they are fine-tuning it. So we cannot build something that is just geared toward one system only and then can do one thing only. It needs to be versatile. Second, now if we start discussing a bit regarding how it works, there are two. Let's say the machine will be linked to the wall. In the wall, there are two outlets, which are the medical air and the medical oxygen. The machine will take the medical air, go through a pressure regulator. The same goes for medical oxygen as well. Then they go through valves into a mixing chamber. This is where we do the mixing to make sure that the amount of oxygen required by the physician or by the healthcare provider is the amount that we actually deliver. After the mixing chamber, it goes to a variable flow valve, and this is something that we designed from scratch. It's extremely important to look at this particular feature, because this is one of the items, or let's say one of the parts of the machine that is going to be very hard to source going down the road, because there are very few. They're being bought by international companies that do medical devices, and therefore they're very difficult to source. Then you go from the pressure regulator, of the flow regulator, motorized flow regulator, into sensors to measure the flow, to measure the pressure, and then into the patient. Now this is the inhaling. So we're pulling air inside the patient. The patient inhales, and we have the exhaling. As soon as the patient will exhale, the valve that is supplying the air will close, and the valve that is on the exhale part, there is another valve that will open. And this is where we monitor the air going out. When the air coming out reaches a certain point, which is the pressure inside the system, so we're looking at the pressure inside the lungs of the patient, this is typically called the PEEP level. The physicians will call it the PEEP level, which is the minimum pressure that they would love to have inside the lungs of the patient, because if we empty it completely, we could have a collapse of the lungs. So they keep some pressure inside the lungs. So we monitor this pressure, we monitor the flow, and we close the valve at the point to keep the pressure inside the lungs. So from there, this is typically how a ventilator works. It will monitor the pressure, it will monitor the flow. We talked about pressure control, we talked about volume control. To be able to reach those controls and reach them properly, we need to be able to measure it, because there are plenty of designs that estimate it. They estimate that this is how much volume that we're putting into the patient. We were adamant to have a redundant system where we have two sets of measurements on the inlet and on the outlet to be able to measure how much we're giving. So we measure the pressure, we measure the flow. This is extremely important to make sure that we are giving and delivering exactly what is required. I think in a nutshell, this is how it works. I'll leave the floor to Dr. Ali. We'll go over probably the 3D model, the whole design, how it is done, and then we can continue.
Hello. Yes, thank you, Paul. What I'm going to do now is I'm going to go over through the design process, how we went from starting with the first initial trial and how we went to the final design, the steps that were taken to transform the ideas that Paul was talking about from a flowchart to an actual product. So for that, I'll be sharing my screen. All right. So what you see here is the final design. This is the final product that we arrived at. But before we got into this final design, what we're using here, we're using a 3D modeling software that we use in order to do a virtual design. We don't want to get the parts and start to see how to tinker with them, how to assemble them by hand. So what we do is that we get the parts, we import it to the software, and then we're gonna assemble the parts to see how they work. So what I want to show is that design process does not start like this. We first start with the components placed in just roughly an estimate how we're gonna go through it. We go through several iterations similar to the one that you see. Just one second. Okay, so sorry, I was showing this. So we will go through several designs similar to the one that you see over here, and after that we get to the final design. So this is the final design. To show you what's the inside of the final design, what is it comprised of? These are the internals of the final product. So we have different components. We have the accumulator, which is used in order to accumulate the air, the two types of air that Dr. Akle talked about, the MA and the oxygen. They will both go through the inlets that you see over here. We have pressure regulators where we control the value of the maximum pressure that can be allowed to go into the regulator. And then we have solenoid valves that control this process. And I need to reiterate what Dr. Akle was saying. If you look at this design, this is the simple design that's made out of components that you buy off the shelf. So these are industrial solenoids. This is 1, 2, 3, and 4 that you get off the shelf. Same goes for the pressure regulators that you see over here. And the only parts that will need to be fabricated is the accumulator, and we have to 3D print like a couple of components, which are the sensors that Dr. Khoury will talk about later. We also need to fabricate a part for an important component in the system, which is the flow regulating valve. This is very important because, as Paul was saying, we do not need just to control that the amount of pressure that's just going to the lungs of the patient. Once the pressure is accumulated inside the accumulator throughout these two solenoids, what we will do is that we have to control the value of the flow that's going to the patient through this outlet over here. This is the Venturi that will measure the flow, and we control the flow through using this servo motor that you see over here. So the servo motor is attached to a simple ball valve. So I will hide this to show you what is this made of. So this is a ball valve that we control with the servo motor. So if we want to allow more air to go into the lungs at the different rates, we have a special type of control algorithms that we use in instrumentation and control. We have a PID controller attached to this servo motor, so that we will be able to control the flow of air into the lungs of the patient. And after the patient inhales the air, the mixture that we got from the oxygen and from the conventional air, he will have to exhale. So we also control the exhale process by this solenoid. So this goes into the patient, and this goes out of the patient. So as we mentioned, we had to have like some parts that you can get off the shelf. If you now go ahead and look at the available market for flow sensors, you will never find flow sensors, or will find it with very limited quantities, because all the world are rushing in order to build ventilators. So flow sensors are we cannot use off-the-shelf flow sensors. That's why we had to design our own sensors, and this is what Dr. Khoury will talk about in a minute. Okay, so this summarizes all the components inside the parts, inside the ventilator. We have the pressure regulators, and yes, an important algorithms that we're going to talk about are how do we control and how do you instrument this system. If you look at the components, we only have solenoid valves and we have a servo. So the solenoid valves are controlled from the controller. Right now we're using a standalone off-the-shelf controller that's called Myrio from National Instruments. So the Myrio will control when and for how long should each one of these solenoids open. So the solenoids will just open and close, but unlike some of the ventilators that are in the market, we do not need to just control the on and off. We also need to control the flow, and this is done using this variable flow valve that we have built over here. This is designed. We have designed this variable flow valve. So with the variable flow valve, we have a closed loop. We read from the sensor that we have designed the amount of flow that's being fed into the lungs of the patient, and based on that, we either close or open the valve in a fast way or in a slow way. So as you're going to see in the demonstration at the end of this presentation, we can control the flow, the volume that's being fed to the patient, the respiratory rate, for how long do we need to, the respiratory rate and the inhalation and exhalation time. All these are variables that we can control. We can also control the amount of oxygen that's being fed into the lungs of the patient, because unlike other ventilators, in our design, we had to come up with a solution in order to control the amount of oxygen without using complex flow valves, because we want our system to be compact. So that's why we also had to resort to Dr. Khoury, who helped us in the design of the accumulator and in the design of the sensors. So this would summarize the design process, the steps that we went. And now Dr. Khoury is going to talk about the design of the Venturis and the design of the accumulator. So Dr. Khoury, the floor is yours.
Thank you, Ali. So basically, as Ali was mentioning, we had really problems, acquiring medical devices because of this pandemic. They ran out of the market, so they were not available. So what we really did was to go and design our own flow sensors. So what we did is we replaced the flow sensors by Venturi design, which are like either readily available or you can print them yourself. So what we did is we printed them ourselves using 3D printers, And now we converted the flow measuring devices into a pressure measuring way of approach. So what we did, we also ran CFD, computational fluid dynamics, to make sure that the system runs with the minimal flow resistance. So this, circumvented the problem of using the flow sensors. So we had no problem doing this. The second thing that we have done is we use the accumulator. The use of accumulator is mainly for proper flow mixing. So if you want to mix oxygen and medical air, and you set a ratio, you need to make sure that ratio is accurate. So what has happened? We designed an accumulator, and what makes the design so special is that we use the pressure sensors. So per se, we had a certain pressure, and we used the system, the accumulator gets depleted somehow. So with a certain ratio, we made sure that we computed the pressure difference needed from from the mixer to the point where we get the maximum pressure required. So in other words, you deplete the accumulator, and then you say, I need 30% of mixing oxygen and air, and we start by measuring the pressure. So we set a certain pressure that maps to the 30% of oxygen and air, and we monitor the pressure. So we given, let's say, oxygen at first, and then we move into air to obtain the proper mixing. So this is what we have done really with the accumulator, and we have obtained like about a 2% sort of error. So this was highly accurate. And now we're gonna move to the safety with Paul, and later on I'll go over the tour and show you these components in details.
Hello again. Okay, one of the issues with ventilators, obviously, is those ventilators are typically used with intubated patients. Obviously, there is the non-invasive ventilation as well. So that would be when the patient becomes a bit better and doesn't need to, and he can breathe on his own, but he needs help. So that would be the non-invasive ventilation. It doesn't need to be intubated, and also you can be intubated and awake as well. But mostly the issue is that if the patient is not awake, then the ventilator typically is the driving force behind him breathing. So any mistake in the ventilator or any problem with the components of the ventilator could lead to injury. So from the get-go, we designed our system to make sure that it follows the most strict safety rules possible. So in that intent, we used the same, let's say, approach that the commercial ventilators would do, using a open valve for the exhale, which means that if the patient, for some reason, there is a problem and he wants to breathe on himself, by himself, he can. This valve, which is normally open, which means even if you shut down everything, will have a integrated connector to it, so that you could add a manual ambu bag. So if you want to move the patient, if there is a reason for that, there is also no problem, without having to completely disconnect the machine. We also have a pressure relief valve. This is a mechanical pressure relief valve. It is required. It has to be there. This pressure relief valve would automatically open as soon as the pressure reaches 60 or 65 centimeters of water. The human being can withstand normally 80 to 100 in one shot, so if it will not injure him, and that's very important. And all of these are actually the redundant part, because there is also the software safety features, which are, since we are using redundant sensors, we're using pressure and flow sensors on the inhale and pressure and flow sensors on the exhale. This is very important. A lot of designs, even the Imperial College design, which was lauded as a very good design, was using only one limb. So the pressure sensor, the flow sensor are only on the inhale, and in our opinion, this is very dangerous. because one of the important parts of safety is actually measuring the inhale versus exhale. So if we have a leakage, if there is some reason that some leakage is inside or outside the patient, we'll be able to detect it. If you have only one pressure sensor, one flow sensor, you can only detect either the inhale or the exhale. We'll be able to compare both of them so we can see, we can give more information to the healthcare provider so he can also analyze and notes whether there is a problem, whether it's a physical problem with the patient or whether it is a problem with the tubes or the intubation is not correct, it is leaking, and so forth. So this is regarding the safety from the mechanical and electronic perspective. We also went a step further. We added a redundant monitoring, let's say, a board that will monitor the number of breath only, and that will monitor the electrical supply on the machine. This is important. It is outside the main controller, so that it's actually monitoring the main controller to make sure that the main controller doesn't have a problem. If there is a wire the problem with wiring inside or something like this, we will know automatically. One additional thing, we added also a battery, a UPS system inside the machine. This was very important because we have to take into consideration that if for some reason there is a power breakdown, it might take more than half an hour to be fixed. So we're aiming at an hour and a half of autonomy completely on its own. I think this wraps up a bit the safety aspects of it. We were very, very keen on making sure all those things are taken into consideration. Every single 3D part that is connected to the airways is going to be coated to make sure that we don't have degradation over time. All the industrial part are biocompatible, and that's very important because we went through multiple iterations. We're using PVC, then we changed that up because it turned out that even though it is safe at so low pressures or pressures that low, we said no, we wouldn't go with something much more, let's say, robust. And so all the parts in the system are actually biocompatible, and they're heavy duty. They're rated for hundreds of thousands of cycles, and this is very important because we need to make sure that the machine can run continuously over weeks and months. I think that wraps it up. I'll get back to the actual machine. I hope you're being able to see it. So this is the machine being taken apart of this thing. It's not in the box, so that you can see the various parts. I'm going to see it.
Are you okay? So
let me get there. Okay. So here we have the flow regulator. Okay. The inlet valves. So one is for the MA. You can show them here. So this one is connected to the oxygen. The other one's connected to the medical air. Then we go to the, as we said, the flow regulator to make sure that the flow, whatever happens in the medical air from the wall, does not affect the machine. So the flow regulators will cap the pressure regulators. The pressure regulators will cap the pressure going into the machine. Then we have the valves, and then from the valves we have the accumulator. We do the mixing in the accumulator. We have the pressure sensor that is monitoring the pressure inside the accumulator. This is to go back to what Michel just said, that we're monitoring the pressure to be able to precisely monitor or precisely control the mixing inside the chamber. The chamber plays another role as well, which is to make sure it provides a stream of air that does not go up and down in pressure. This is very important. And then from there we go to another valve, which is the inlet valve to the inhaling system. We go from the inlet valve, we go to the flow regulator. This is the motorized flow regulator that we designed. You see it's 3D printed. The parts are 3D printed here. Then from there on, we go to the Venturi valves. This is where we're measuring the flow, and we're measuring the pressure as well. So we're measuring the flow going into the machine, going into the patient, and then we're measuring also the pressure going into the patient. So this is the pressure, as we can see here. This is our dummy patient. I hope you can see the yes. So there you go. You can see the patient breathing. This is the intubated dummy. It is simulating a real patient. Then we have, as you can see here, this is called a dual limb system. It's extremely important to have a dual limb system. So one for the inhale and one for the exhale. Here we did not set up the filters, but you would have filters installed here to make sure that the machine is 100% safe and it's clean. Nothing is going to go into the machine and eventually cause infection in subsequent patients. This is the return valve. So this is the return limb, the exhale limb. Again, we have pressure reading, flow reading again into the exhale valve. So this is the control system. These are the electronics that control the system. Typically, as we said, the system will be supplying air through the flow valve into the patient and exhaling from the other side. As soon as the pressure sensors or the system, the control system, detects that the pressure has reached the level required, we're talking about exhaling, the PEEP level required. So if we're exhaling from 30 centimeters of water to 5 centimeters of water, which is the PEEP level, as soon as we reach the PEEP level, the valve will stop. Obviously, this is simplifying things because we take into consideration a lot of things regarding calibration of the system, the calibration towards the patient, which is automatic calibration for each patient. But the point is, it will keep pressure as required by the healthcare provider inside the lungs of the patient to prevent them from actually collapsing. Can we put that? Yes. Okay, we're trying to share the screen of the actual control. Just a second. Okay, you got it. You got it. Okay, I think now you should be able to see. Okay, perfect. So this is typically the machine running, and this is the screen, and you would automatically recognize the same waveforms that we see on commercial machines. Obviously, just to be clear, the dummy being used right now cannot simulate 100% the human being, and so the waveform will differ a bit. But typically, what you're seeing here is the system running and adapting to the patient and trying to reach the pressure level that is required. You can look at the accumulator pressure. We can see the inhaling pressure, the exhaling pressure, reaching the levels that we want. We can see the accumulation of volume inside the lungs of the patient, and as we can see that, we can look at it and we see this going smoothly. This is not an open closed system. It is smoothly applying air to the patient's lungs to make sure that it is not going to in any way be discomforting for the patient and achieve the volumes required. Remember that the lungs of the patient are viscoelastic. If you bring in air far too fast, the pressure buildup will go up and he will never get the volume required. So this is why the system is a smart system that will actually adapt according to the patient to be able to give him the amount of volume required without reaching high peaks of pressure. We can also see the flow, and these are being what you're seeing now on the screen are coming from two different sets of sensors and for pressure and flow. As we just saw you with the video, we're reading from both sides, and this is where we're seeing that the system is working properly because we don't have a disconnect between the inlet and the outlet, which is the inhale and the exhale. I think that wraps it up. Hey, Ali, can you pick up here for instrumentation?
Okay. Yes. So just the last thing that we were going to cover is some of the control algorithms that were used in this software. So here we're using LabVIEW in order to control the process, and in order to achieve the proper pressure values, we had to use PID controllers. So the PID controller will check the feedback for the sensor for the PID controller comes from the inhale pressure sensor. And based on the value of the inhale pressure sensor, we control the opening and closing of the valve. So by that, we guarantee that the amount of air that's being fed, it's the volume is properly controlled. Yes, so Dr. Ali, if you can show us the block diagram for this, if you want. Okay. So what we do is that we have a couple of loops, each one controlling the process. We have the control loop that's below is used to control the inhalation process. So we make sure that we always hit the target pressure and the target volume as well. So it's not only when I reach that pressure, I will stop. I will have to make sure that the patient has, for example, if we set the target volume to be 400 milliliters, the amount of air that will be that will go to the lungs of the patient will be controlled. So we control the volume, we monitor the pressure, we make sure that the pressure does not exceed the final, the maximum pressure that's allowed. So that's a safety thing. So if we get to the maximum pressure, we will stop the process and make sure to sound an alarm. Another thing, we have a mechanical we have a mechanical device that will discharge the pressure if we reach a higher value as well. And for the accumulator filling, we also have a simple control algorithm that we can be using to control the amount of oxygen that's being the amount of oxygen mixture. So this is in the accumulator filling that Dr. Ali is pointing at. And yes, so all these, what you see here, it might look simple, but it took a lot of time in order to get to the final design of the algorithm, design of the software, the state machine architecture that we're using. So these are some of the control aspects of the software. We also have some calibration process that we do to the flow sensors, because the flow sensors on their own, they will just tell you the pressure difference. So we also had to correlate the pressure sensors values into actual flow readings. So we have this other software that will do the calibration. So at the end, this machine will be able to deliver the requirements according to the standards that Dr. Ali started talking about. We'll be able to control the pressure, the volume. We have different operation modes that we can switch into, and we also control the oxygen, the FiO2 mixture. So this should summarize the instrumentation part of the project, and I leave it to my colleagues for the final words. Dr. Ali.
Great, thank you so much, everyone. I think it's now time to have some questions and answers. Feel free to, I think there's a Q&A. It seems there are some questions that are being asked at the time being. If you want, please feel free to ask any question, whether it is a general one or more of a technical question. I know there's so many engineers attending today, so we'll be happy also to entertain the technical questions. So Christian, it seems he's interested in nargile smoke exposure and cannabis smoke. Maybe see how we can build a device to reduce those, right? Another question is, device supports both assisted and controlled ventilation. Yes. Okay. It can assist the patient in breathing and can also complete control over the breathing process. Yes. So it can be operated either way. Basically, it's either because the patient can have two different stages, whether fully sedated or partially sedated. So basically, if the patient is fully sedated, the patient paralyzed actually, so the patient won't cough, won't have any issues. This is the case where you put full control, and it's probably the easier one, because all what you have to do is to make sure you push a certain amount of air and you recover that amount of air in a certain duration of time. However, in assisted, this is more critical, and this is where actually we move. This is actually very important to take out the patient from the disease. So usually the phase that the medical doctors told us, especially Dr. Faiz, was insisting from the beginning. He said, okay, usually with COVID-19, we fully sedate, we fully paralyze the patient up front, and then for a few days, or hopefully not more than that, the patient will be completely paralyzed, will be fully controlled by the machine, and then after that, there is if the patient improves, there is a cycle where we are taking the patient slowly out of the ventilator, and this is where they use assisted. So assisted is the patient will try to be breathing on his or her own, and they may cough, they may do all these things. The sensors, the pressure sensors that we have, will try to detect those and will actually push air and take out the air as the patient would like. How many ventilators we're expecting to manufacture? Yeah, as Ali said, it depends on the situation. Actually, we're just making it open source. Anyone in the world, be it in the US, in Brazil, in Italy, and I don't know, Singapore right now is being hit badly. If anyone would like to use it, we are going to publish the blueprints, the codes. Everything is open source. Everything is easy to replace, even the parts, because we're using pretty standard industrial parts. So we personally in Lebanon, I don't think so far people has been doing really well. We as Lebanese, we're really committed to staying at home. We had good social distancing. We're following good hygiene, and we're actually doing pretty well on that. So so far, I don't see any need for being, for ventilators. I mean, we're pretty lucky, and hopefully we won't have a bad round 2, so hopefully we'll never need it in Lebanon. How much time did the design and coding took? Okay, how we started to think about the code. Oh, Dr. Ammouri is laughing. So Dr. Ammouri, by the way, is always online. He never joined us but once. So this is why he can laugh, because he's the one who, he did most of the code and he did it remotely. And this is actually a very nice engineering example where things happened really remotely. The CAD was done remotely, and some people manufactured remotely, we coded remotely, and just the three of us, Paul, myself, and Michel, were close. So it took us about a month, I would say, of really good work to really put the whole thing together. It's pretty complicated. The code is very fancy, and it can go, you want to make sure it won't go wrong, because again, we're dealing with people's life in here. We want to save life. It's not that simple. Everything you have to think about everything from an engineering perspective. What could go wrong? A relay could go wrong. A solenoid could go wrong. A controller could go wrong. So in the final design, which we did not implement at this stage, S&AS is implementing, there are 2 watchdog controllers that are watching the main controller and making sure it is working properly. If the main controller fails by certain signals, like certain pressure signals fell or something like that, the watchdog controllers will take over and will try to sound alarms, will do everything necessary. So these are electrically independent systems to make sure that no matter what happens, the machine will not kill any patient and will end up hopefully saving lives. So too many questions. Will you post online a detailed diagram of the prototype? Yes, this is the aim. Actually, we're trying to publish it fully, along with diagrams, codes, everything. We will be working on that. So yes, this is a fully open source project. Did you implement redundant controllers? So we did not implement them yet, but this is what S&AS is currently working on, and hopefully within a week or so we will have the full design for that. Okay, does this system account for change in oxygen level in incoming O2 or air supplies? So no, we're not measuring FiO2, because again, the sensors that measures FiO2 are pretty medical, especially the oxygen sensors that work in the range of our interest, and they are going out very, very fast. So for that reason, we decided to work with pressure. Now we know oxygen in air on our planet is 21%. It can vary a little bit. I mean, it's not going to vary more than 0.5%. So based on the pressure, we fill with a certain amount. We have the equation, PV equal nRT. We start with that. We know how much pressure drop we have in the accumulator, and then we add the oxygen that is required, and then we completed that with air. We know air on planet Earth is 21%. So based on that, we have all the calculations. So no, we're not measuring it directly, but we believe this is more than enough. We will be running tests shortly also to validate all this, and we're seeing less than 1 to 2% error in terms of our calculations. Did you think about doing a huge ventilator and could be distributed to many patients? No, we did not consider that. It seems Paul have a different answer, so maybe this could use.
Typically, the problem is any approach that goes through actually using a one ventilator for multiple patients. The pre-requirement for that is that all the patients are physically or clinically the same. This reduces greatly the possibility of using in multiple environments. What's being done now is that some places, when they are out of ventilators, they are using one ventilator with some kind of splitter to be able to provide for multiple patients at the same time. But there is no way of controlling all those things that we talked about before, which is controlling the flow coming in and out for every single patient. We're controlling the flow being supplied to the whole system. So to 2-3 patients at the same time. If one patient is breathing a bit more than the other, pretty similar in nature. They're pretty similar in nature, they're pretty similar in size of lungs and so forth. And usually when they're completely intubated, completely sedated. So they're, in a nutshell, filling up a balloon or 3 similar balloons. So this works to a certain extent, but should not be let's say, a target for us. Back to you, Barbar.
Thank you, Paul. Someone is asking about is the clinical simulation enough? Actually, I believe it is, because we're simulating on several mannequins. This is one mannequin we're simulating on. We have multiple models for lungs, and actually we're going hopefully to AUB-MC in a matter of 1 week or 2 to really test. They have a full-fledged lung prototype system, so we will be testing there and make sure that it works fine. And we've been testing reliability. We've been testing how clean it is. We made sure all our components are medical grade, so mostly stainless steel. They have no PVC in them. They can handle the oxygen because oxygen is pretty corrosive. So all these components are being tested. We believe this ventilator should be enough. Again, the main drive for doing these ventilators is not commercial. We're not trying to have a company and get FDA approvals and do the whole thing. We're trying to meet the standards. We try to meet all the standards of the British government, and currently there is a committee working on the Lebanese standards, and definitely we will be meeting those. So once all these have taken place, I believe it could be tested directly on patients whenever it is critical. I'm not going to remove a patient from a good ventilator that is fully proven and fully put it on this. But once we get to the point where we're doing triage, and hopefully we will never get there, then I would rather, yes, put a patient on this ventilator, and I think we will be confident doing that. So the cost of the ventilator is between 1,500 and 2,000. So why ventilators are expensive? Because, you know, people like to make money, of course, and then there are more testing going into them. They actually are built in clean rooms. They also are a little bit more sophisticated. So there is quite a bit of sophistication levels that they could do. Maybe this ventilator cannot do. However,
Yes,
we believe what we have is sufficient for COVID-19 patients.
Yeah, I was saying.
What is the most important thing that distinguishes this ventilator from others? Well, it all depends on what are we comparing to. If we're comparing to commercial ventilators, of course, availability, because we know current manufacturers cannot manufacture if there is if people did not respect social distancing, the curve of COVID-19 would have been in the hundreds of millions by now. So we would have so many patients out there, and we wouldn't be able to really catch up in terms of ventilators with those patients. As it happened in Italy, people were going through triage. Some people were decided you go home and die, okay, because you don't have a good chance. So this is where these ventilators are useful. Now, compared to other designs we've seen, we've seen in Lebanon alone 10 or 15 designs. We've seen across the world maybe hundreds of designs. This is a very sophisticated design. In my personal opinion, I am convinced with only 3 designs so far. This is one of them. NASA has a really good one, and Tesla has a good one. So these are the 3 designs that I believe are at the current time able to save lives. They do the whole process, they meet the requirement, and they are actually open source. Does the material used in 3D printing medically approved? Yes, we verified that. So what is the most important thing that distinguish, okay. Does the cost mentioned include the controller MyRio? Actually, yes, it includes it. It includes the lower price, which is the student price. Okay. Did Biomedical AG collaborate in this project, or was the communication directly between you and the medical staff? Actually, we had one biomedical engineer with us. We had Jamal, right? And George, right? And Ibrahim Isa. So we have Wissam Jalwan and Ibrahim Isa, and actually we have Bassam Tabshouri, who's also a biomedical engineer at LAU BMC. On the Slack group, we had so many valuable contribution. Now, they were really instrumental, especially in the beginning, in the initial phase where we are really putting the whole design together. I mean, as engineers, without this experience, we wouldn't know that certain things would work on patients, others would not work on patients. So they were very, very helpful. Of course, the medical staff was also extremely helpful because they are the end users. They know exactly what is needed. Could your ventilator be put into production in Lebanon? Of course, yes. Polytextile, Paul can work on that with S.A.S., and this is the goal. So yes, definitely we can if needed. And actually, we can scale it up very much because, as Dr. Ammouri mentioned, most of the parts are either 3D printed or locally sourced. They are available off the shelf. We did not really do much, try to use much parts that are pretty complicated to manufacture. So yeah, there's the Medtronic. The Medtronic design is pretty nice. Of course, this is a really full-fledged ventilator, but if you want to try to go there and try to build it, the problem is you will not find the parts. So this is why what distinguishes, again, this ventilator from the commercial Medtronic one is that you will be able to find the parts off the shelf. So what should the user input to the ventilator? Okay, the doctors decide on a few parameters. One, the oxygen level, FiO2. They also decide on how many breaths per minute. What we had set up, what we showed you was 12. It usually goes anywhere from 10 to 20 or something like this. Can't remember the numbers. They also decide per breath. So let's say we selected 20 breaths. So every 3 seconds you have a breath. In this 3 seconds, what happened? Usually the way it goes, around 0.8, 0.9 seconds for the inhale, and about the remaining time, 2.2, 2.3 seconds for the exhale. So this is what they decide on. Also, they decide whether they wanted pressure controlled or volume controlled. They decide if they wanted assisted or not assisted for fully sedated. So these are the kind of option a medical doctor will input to a ventilator. What will be the cost of our proposed ventilator is about $1,500 to $2,000. Did we use zeolite material as filter sieves, or it's not required in this device? I don't know about the filter material. We're using the commercial filters that usually comes for any ventilator. They are abundantly available. We don't need more than this. Comment about the ventilator by Isaac. I think it's an MU bag. I guess Robin is here, so it means my time is out.
I'm just looking at
the floor is yours. Thank you, everyone.
There's around 60 questions or so, but I'm afraid, guys, we have to wrap up at 5. تعودت online نبدأ sharp at 4 ونخلص sharp at 5. But nonetheless, if you still have any questions about anything that was presented today from all of our 4 colleagues in Michel, Ali, Barbar, and Paul, please look their emails up على LAU website and so on, and you can send them an email. أنا عم بتبرع بخدماتهم من هلا لكم. They will gladly respond to you regarding anything. أكيد apologies that we're not going to continue with more of the questions. لأنه I can see some